Hello, my name is Evie, and I'm a first-year engineering student studying creative technology and design at the University of Colorado Boulder. Today's lesson is all about mathematical modeling, and I have HelperBot here, who's very good at math, to help out. Mathematical modeling can be very useful in the real world. It helps us be able to visualize, analyze, and even predict data or information in the world. I'm sure everyone has seen a graph of some sort, right? Well, we'll mostly be taking a look at scatterplot graphs in this video. If you're unfamiliar, they look something like this. HB? Graphs like these can be very helpful in modeling data. However, we can make it even more useful by applying some linear approximation. Let's jump right in. Here's a graph about the relation between a plant's water intake and its height. We have two variables here, how much water we're giving the plant in milliliters, and the plant's height in centimeters. The independent variable is the variable that we are changing. In this case, it is the amount of water we give to the plant. You can see the units here at the bottom, on the x-axis. Meanwhile, the dependent variable is the variable that we are measuring, the one that changes because of the independent variable that we are manipulating. In this case, it is the plant's height, which we are measuring. You can see the units here to the side, on the y-axis. You may notice that the data points on the graph seem to be all over the place. So how can we make a linear graph out of this when it's impossible for the line to pass through all the points? Well, we can do this with a linear approximation. Take note of the approximation part. The line won't be exact, but it shows us a pattern that the data is taking with a line of best fit. Here you can see that as the amount of water is increased, the plant's height does as well. The data points follow a rough positive line upwards. You can draw a rough approximation line by just eyeballing it, but we also want something a little more accurate, so we can look at predictions later on. How do we do this? Well, I'm glad you asked. HB, how do we do this? Oh, right. First, we want to find the slope of the line. Then, we use the point slope formula, or y equals mx plus b, to plug in the slope and a point of interest to find the y-intercept as well. Then you'll have your equation. We can predict things about the data with an equation like this. Now I know that was a lot, so let's walk through a problem together. Here's the graph about plants again. We need to find the slope, which is rise over run. We can do this by finding the averages of all the y values and dividing them by the averages of all the x values. For this graph, the slope should be 1.04. Once you have your slope, you plug it into the point slope formula, or y equals mx plus b. In our case, this will be y equals 1.04x plus b. Now we need to find b, which is the y-intercept. In order to do this, we plug in one of the points that we think will give us the line of best fit. This can be called a point of interest. You can mess around with this part to see which one will give you the line of best fit. Then you can find the exact value of the y-intercept afterwards. In our case, we would plug in the point 4, 5, so the y-intercept would be 0.84. Now we put the formula together, and we get y equals 1.04x plus 0.84. We can use this formula to predict later outputs, considering the scatter plot here follows a general trend. For example, we can predict what a plant's height will be if we give it 10 milliliters of water. If we plug this in and solve, we can see that the plant will grow to 11.24 centimeters. Did you know that there's another method to find the slope of the line of approximation? It's called the least squares method. It allows you to calculate the best line of fit more accurately than before. It tries to find the minimum vertical distance between the data points in the line of regression to adjust the line until it fits the graph accurately. However, this method is a bit complicated to do by hand. You're better off asking a robot to do it, huh, HB? Haha, yeah, you're the best at math. There are many things we can use this for in real life as well. There are lots and lots of scatter plots out there with all sorts of cool data. It can range from the correlation between a robot's battery speed based on its battery power, to the ocean's water level throughout the years. Again, approximate linear models can help us see the trends in the data, like whether it's positive or negative, or if the slope is changing quickly or slowly. It is also great at predicting outputs with different inputs. While it probably won't be the exact value, since things in real life don't typically stick to an exact pattern, it can still be pretty useful for a general estimation. For example, you could see how much a computer might cost a couple years later based on how its prices have been going, or how the size of an iceberg might change after a few years as well. There are many useful applications that we can use linear approximation in, and now you know how it works. Linear approximations can be helpful, but they don't solve everything with scatter plots. Think about the benefits of linear approximation and what they are. What about the limitations? Now think about how you can use this in your own life. If you've ever wanted to predict the outcome of a scatter plot, linear approximation is the way to go. Anyways, that's all for today. Thanks for watching, and we'll see you next time. Check out the full lesson on the TeachEngineering website. Then, test your knowledge of linear mathematical modeling by collecting data and making a model from a linear approximation in Judgment with Jelly Beans.